Hello, my name is Tomáš Pevný, and I would like to introduce you to a JsonGrinder library. The motivation for the library is popularity of structured file formats like XML, JSON, protobuffer, or message path. These file formats are great because they allow you to describe samples or data with increasing level of detail. They also allow a lot of flexibility. On this example, we can have a small sample 1, which comparing to a sample 2 misses the service key. Similarly, the sample 3 comparing to sample 2 contains more items in the list under the key services. And this flexibility means that you can have very small samples like sample 1 and very large samples like sample 4. If you want to perform a machine learning on this data, you have few approaches which have been seen in the literature. The first one is feature engineering. You take your data and you describe them by a set of features of a finite dimension, and you stick it to your favorite machine learning tool like random forest. The other approach is to take JSON, treat it as an image, and then use the plethora of machine learning tools designed for digital images. Of course, you need to crop and resize the image such that all images are of the same size. The other option is to take the JSON and treat it as a text, which with the rise of popularity of large language models might work, but we have not tested that. The other approach is to take the data and treat them as a heterogeneous graph. This is a good option in our opinion, but you will have trouble with scalability, and we are not aware of a good library that would be suitable for that. And the last approach is the HML, which is an abbreviation for hierarchical multiple instance learning problem, where the JSONs are treated as JSONs. So let me now introduce how the HML works. The core idea behind the JSON is the observation that JSON contains 3 types of elements. There are leaf nodes, which are typically numbers and strings. There are arrays, for example services, which can contain arbitrary number of items, including 0. And then there are dictionaries or key values, as for example the item of the services, which contains dictionaries containing port and protocol always. And the idea behind HML is to design an element which take the representation of their child, which are considered or which are assumed to be vectors, and project them to a vector. By this design contract, the HML knows that child can be always represented as a vector by some projection which is optimizable. So let me demonstrate it on an example. We have the example as we had before, and first we will try to project the values of the port to some fixed dimensional tensor. And this is very trivial. In this case, we will treat the ports as a number, and therefore they are represented by a one-dimensional tensor. Next, we will try to represent the protocol, and because in our data we have only 3 types of the values, TCP, we have only 2 types of the values, TCP and UDP, we will represent it as a one-hot vector containing 2 values. And we will do the same for the rest of the leaves. So for example, the items of the MDNS services would be represented as strings, and similarly the IP addresses and MAC addresses. Now comes the first hurdle. We need to represent a dictionary as a vector. We know that the dictionary always contains port and protocol, and we know that the port is a single-dimensional tensor and the protocol is a two-dimensional tensor. So we will just concatenate them side by side, and the output of the services can be a three-dimensional tensor. And we can do it for the rest. So this is easy and this is well known. The last thing that comes to play are arrays. To represent an array as a fixed dimensional vector, we know that its child or its items are already represented as vectors, and we just take an average, an element-wise average or a maximum, and that's it. So now the services can contain arbitrary number of items, and they are always represented, the output is always represented as a fixed size tensor. And we go further, we do the same for the MDNS services. We concatenate all the items from the top-notch directory, from the top directory, and we are done. The sample is now represented as a vector of a finite dimension, and we can use the usual methods to classify it to selected classes or desired classes. Well, you should now ask, where are the weights? Well, each array can be, or each array represents a feed-forward neural networks, but notice that feed-forward neural networks are always special for each type of the value or a node inside the JSON. So for example, all ports will use feed-forward neural network 1, and all protocols will use feed-forward neural network 2. Their concatenation, that means the items of services, would use feed-forward neural network 3, and so on. So on the end, you got to a feed-forward neural network 9, which provides the classification. And the beauty of this construction is that it's completely differentiable, and you can use your favorite tool to optimize the parameters. So we usually use stochastic gradient descent, and each neural network F is a feed-forward neural network. JsonGrinder library. This script creates a classifier for mutagenesis data. And I think about the JsonGrinder is that if you want to switch to a different problem, you just need to change the source of the data at the line 9, and the rest is automatic. This gives you the default performance shown in the middle column. Of course, this default performance is inferior to the state-of-the-art shown on the right-hand side, but it's typically good baseline. If you start to tune the building blocks inside, that means the neural networks, by changing different number of neurons or layers, or changing the nonlinearity, you can further improve. I would like to invite you to a JsonGrinder library, which is available on this address. We would also very welcome contributions specifically on optimization of the neural networks inside the classifier. Thanks a lot for your attention.